All right. So let me share the screen. Here you go. So we discussed first 10 problems so far. So these are calculus, practice problems for calculus. Um, so we discussed how to draw a graph, and question number 9 and 10 also we discussed in our last video number 3. So this is the final video, actually, video number 4. Okay. So I'm going to discuss this video contain, you know, integrations. So everything about integrations that we discussed in calculus. Okay. Um, so, if you see these questions, the first question number 11, is you need to know, basic integrations, definite and indefinite integrals. Number 12, you have to use fundamental theorem of calculus. Number 13, mainly you do integration using substitution. Okay, there's no integrating by parts or integrating using partial fractions or anything like that. So the integration using substitution is the place where we stop the course. Okay, right. So question number 11. Let me see. So I'm going to do that in this space, and I complete the question and I erase and start the next second one and so on. Okay. So normally when you have um, integration 7 sine theta over 3 d theta, so you have to think about what is the integration of sine. So integration of sine is negative cosine, because the derivative of cosine is negative sine. Okay, so it's cosine theta over 3. The 7 is just a constant. You can take it out from the integration, so 7 stays like that. But think about that. So if you differentiate that, you get negative sine, it should be negative. So negative sine theta over 3, and you multiply by 1 over 3, because you have to take the derivative of this, right? So when you take the derivative, I'm talking about, okay? So when you take the derivative, you multiply by 1 over 3. So when you take the integration, you have to divide by the derivative of theta over 3, which is 1 over 3. So, and plus c. So it will be negative 21 cosine theta over 3 plus c. C is an arbitrary constant. You can check that if you differentiate my right hand side, the answer, you can get 7 sine theta over 3. Okay, because when you differentiate, you have to multiply by 1 over 3, which will cancel out with this, and you get 7 back. Okay, so think about that. So I can give you roughly like, kind of a formula for you. So if you have a sine b theta, if you have a sine b theta, integration is minus a cosine b theta over b. Actually, you have to just divide the angle. Okay, like this, plus c. Remember, you can't cancel out this b with b. Okay, let me see. I should write b theta over. I should be able to cancel out. Yes, because it's like a 70,000. Yeah, so it will look like minus. Wait a minute. Oh, yeah. So I make a mistake. So you have to have everything divided by b. Okay, not just the angle. So cosine b theta over b, not just the angle. Okay. So look at this. I divide entire expression 1 over 3. Okay. This is the formula you can use to have something like that. If you have a cosine b theta d theta, you can write a sine b theta over b. There's no negative in there. Okay. Right. So that's good. So that's part A. I'm going to go to part B. In part B, you can use actually substitution if you want. Because, or you can think, okay, secant square 5x minus 1. You don't need substitution actually. You know derivative of tan is secant square. So you take this tan 5x minus 1. Because if you take the derivative, you can go back to your integrand. Okay. Yeah. But remember, if you take the derivative, you have to multiply by 5. So it's when you take the integration, you divide by 5. Okay. So if you think about, if you take the derivative of the right hand side, it's secant square 5x minus 1 times 5. So that multiplication should cancel with the denominator to get this one back. Okay. So you always divide by the derivative of the inside function when you do integration. Okay. C, you can write it like 2x plus 5 negative 3 dx. So again, here you can use power rule. That means you can take the same linear factor minus 3 plus 1 over minus 3 plus 1. But the problem is, if you have just x to the power n integration, you would do that, right? X to the power n plus 1 over n plus 1. But normally you have to divide everything also by the derivative of x. Derivative of x is just 1. So that's why we don't include that one. But here we must include that. Okay. So we must include the derivative of the inside function, which is 2x plus 5. And you have to multiply by 2, which is the derivative of this. Okay. That's how you complete. So 2x plus 5 negative 2. So this is negative 2 times 2 is negative 4 plus c. To verify, you can differentiate the right hand side. If you differentiate that, you can get this one back. Okay. Yeah. Yeah. Would be fine. Yes. Okay. The next one, 1 plus cosine 40 over 2. Okay. So I'm going to erase part B. 1 plus cosine 40 plus part B. 1 plus cosine 40 over 2. So you can separate it like a 2 integration if you want, like half times dt or dt. Half you can take out and half you can take out, and cosine 40 dt, because it's a plus, so you can separate it, and then you can use the integration for the both functions, like dt. If you integrate dt, just you integrate just 1, so integration of 1 is just t, right? So you get half times t, or t over 2. Here you have cosine. So if you take the integration of cosine is sine 40, and you have to divide by 4. That's the derivative of 40. And you have 2 also there. So it's like multiplication. So you get t over 2 plus sine 40 over 8 plus c. Right? So that's, you can differentiate. To differentiate again, if you differentiate the right hand side, this part, you can get this one back. Okay. Right. So what is the other one? So the other one is definite integral. So I'm gonna, so maybe I'll go down and explain it here. Okay? So I'm gonna explain it here. E. -2 to 4 x over 2 plus 3 dx. Okay. Again, you can take half out because it's like here 2 and -2 to the 2 to 4 x dx, and 3 you can take out and dx, -2 to 4. Okay. And x, if you differentiate x, it's x to the power 2 over 2. If you integrate x to the power 2 over 2, and you put the upper limit, actually you have another half here, this one already there, 4 and -2. This will be 3x, 4 and -2. So if you plug 4, it's like 16. If you plug -2, it's -2 to the power 2. And you have 2 times 2 over there, it's 4, plus 3 times, plug 4 first to your x. And you plug 4 first, and then -2. Subtract negative. And you get here 12 over 3 plus 18. 4 plus 18, which is 20. Right. So that's how you would do it. So let me see if I make any mistake. Let's see. So I think it's everything good. Okay. The power 2 is a 4, the 4 times 16, divide by that. So I have, yeah, 18 here. No division. Okay. Okay. So the next one, part F. Oops. Maybe I'll use, I'll use that one. Okay, but so E -2, oh no, E is just F. Okay. 1 to 5. It's just a polynomial, x to the power 2 minus 3x to the power 5 dx. It's kind of an easy one. So x, just 1, if you integrate, it's just x. X3 over 3, 3x 6 over 6. And you have to plug 5 first and 1 plus 6. The problem is you have to plug 5. But it's okay, you know. Yeah, I can do that. So like you plug 5 first, it's like 5 to the power 3 over 3. This is cancelled out, so it's like 5 to the power 6 over 3. And you have to subtract by plugging 1, so it's 1 over 3. It's like actually 1 over 2. This is like actually half. And now you have to keep, you know, doing the simplification. Since I'm really looking at integrations, it's not huge algebra you have to do, especially in the test kind of test question. I would not ask you something like plug in 5 and find 5 to the power 6. But if you really need to solve that, it's like 125 over 3. It's 125. You have to multiply it by itself. That's like 5 to the power 6. So it's 12 times 30. 3, 156. I'm just plugging those, okay? This is not necessary, but you can, you know, really do it. It's like 6 over 6, 2 over 6, 3 over 6. If you simplify that, it's like a 1 over 6, so minus 1 over 6. That's it. Right, so roughly you can keep it as a fraction. Right, that's question number part F. Okay, let me go and explain the G. These are basic integration where you use power rule, basic sine, cosine integrations, and so on. Okay, right. So let me see. Secant square is again, it's easy. We did it. More challenging one more than that. So it's 0 to pi over 4, right? Pi over 4. Secant square x over dx. I know the derivative of tan is secant square, so the derivative of secant is integration of secant is tan. So if I plug tan, plug 5 over 4, tan 5 over 4 is 1, tan 0 is 0. So it's just 1. Okay. The answer is 1 in this case. H, the last one. So H is little tricky because you have to think about how the modulus x function look like. The modulus x, if I draw, the modulus x function look like this. This is how it look like. So this is modulus x, okay? This part is like x, y equal x. This is minus x. So if you want to integrate that, minus 1 to 1, modulus x is same as minus x. Negative 1 to 0, okay? 0 to 1, it just behave as a x function. So look at this. I stop 0 and start from 0. So that means I'm really going from negative 1 to 1. So now you can take the integration. So x to the power 2 over 2, 0 to negative 1 to 0. This is x to the power 2 over 2, 1, 0 to 1. Okay. That's you have to keep in mind that modulus x is not a one function in between minus 1 to 1. It has two pieces. Negative 1 to 1, the piece is negative x. 0 to 1, you have to consider the piece which is x, okay? So if I plug, this minus is already there. If you plug 0, it's 0. If you plug minus 1, it's half. Minus 1 to the power 2 is 1. Plus, half I can take out actually. So it's like 1 to the power 2 minus 0 to the power 2. So just, it actually gives you half plus half, which is 1. That's the area. Actually, that's the area under this minus 1 to 1. This is a triangle which has area half. This one has also the same area half. Half plus half gives you 1. It's really finding or gives you the area under the modulus x between minus 1 to 1. Okay. Right. So that's first. How many problems? It's like 8 questions, 8 parts. 8 parts really check your ability to do simple integrations. Okay. Number 12. So number 12, you have to use fundamental theorem of calculus. I'll give you the general version of fundamental theorem of calculus, like if you have the function given as integration, let me give you like this. If you have a function y, let's say, given as integration of ft dt, starting from function, let's say gx to hx, something like that. Okay? And if you need dy over dx, we can define dy over dx as if you plug hx, you replace your t variable with hx and take the derivative of h, subtract, you plug the g function for your t variable and take the derivative of g. That's what you really do. So if you have a constant, you may ask, if you have a constant anywhere here, for an example, main you have constant in the lower limit. So G dash is 0. You have a constant, let's say this is like C or A like here, or maybe 1 like here. In that case, you don't have subtraction part. This is a very easy one. Okay, so part A is like a simple version. So it gives you your y is a to x t cubed plus 1 dt. So dy over dt is, you replace t with x. That's it. So it's dy over dt. That's simple as that. It's like your hx function is just x. Replace x instead of t, and derivative of x is just 1. So that's not to worry about. Okay. So how about the other one? So if you have part B, so in this case, y, I can switch if I want. It really doesn't matter. You can use this general theorem if you want, but no, usually I would like to change it to phi to x and use the same theorem that I used previously. Okay, and dy over dx is just minus, and you replace t with that x, 3x sine t becomes sine x, and you can multiply by the derivative of x is just 1. I'm not going to do that, so you can keep it like this. Okay, replace t with x. Part C is a little challenging because you have x to the power 2. Okay. In that case, you have to take the derivative of x to the power 2. Part C, if you want to get dy over dx, this one, replace t with x to the power 2, like here, you replace t with this t, you replace with h to the hx, that's your upper bound, and you take the derivative of x to the power 2, which is 2x. Since you have the lower limit is constant, you don't want to worry about subtraction part. Okay. So d, again, you can change its limit like upper limits and lower limits. 3 to 1 plus 4x squared. It become minus because I changed the lower and upper limits. And if you need the derivative of that, dy over dx, it will be negative 1 over 1 plus, instead of t, I put the upper limit, everything as it is. Everything I replace here for your t. And you have to take the derivative of that. Derivative of that is what? 8x. That's, I put a big bracket here. That's the dy over dx. So that's called like fundamental theorem of calculus. You have function defined as an integral, you can get its derivative simply using that fundamental theorem of calculus formula. Okay. Evaluate the indefinite integral using substitutions. Okay. All right, so I think I'm good. 13. All right. You have to use mainly, substitutions. Okay. Actually, this is not hard if you go step by step. So I'm going to explain part A. So always think about substitution, that the derivative will give you the other part. Okay. So what I mean by that is, for an example here, if you choose your u variable, the substitution as 2x to the power 2 4x, because you have fourth power here, that is why I choose this one as u. And I can write it as u to the power 4. See, then I normally choose it as I because I go with the same integral. Okay. And I have u to the power, I can write this entire thing as u to the power 4. But the problem is I have 3x plus 2 and dx. If I take du over dx, I get 6x plus 4. I need 3x plus 2 dx. So if I take 2 out, it's 3x plus 4. So you can see I can kind of get the same thing, but I can bring 2 down like du over 2, and I have 3x plus 2 times dx. I create that, you see. So here I have this part 3x. Let me use a different highlight. So I have this one 3x plus 2 dx. I create here using my variable du over 2. Okay, so it's in this case it's du, this entire thing 3x plus 2 dx is du over 2. Over 2 I can bring it to the other side. It's really half u to the power 4. So if I different integrate with respect to u to the power 5 over 5 plus c. C is arbitrary constant. And now I can go back to my original variable. It's 3x to the power 2 plus 4x to the power 5 over 10 plus c. That's my answer for part A. Okay. I integrate 3x plus 2 times 3x to the power 2 plus 4x to the power 4. Big, it's a very, actually how much? It's like 9th order polynomial. This is the 9th degree is 9, because if you expand everything, it's going to be very long and has a lot of terms. It's a formula with a lot of terms, but I can quickly integrate it using substitution. Okay, right. So I'm gonna go to part B. So part B, you can see. I'll take time for that here. So 4x cubed over x to the power 4 plus 1 to the power plus 1 to the power 2. Okay, so this is one question. 4x cubed x to the power 4 plus 1 to the power 2 dx. Think about what is the substitution here I should use. Can I use x to the power 3 as something? It would not give me any help, right? So the best choice is x to the power 4 plus 1. If I choose that way, I can replace my denominator. And not only that, if I take the derivative of that with respect to x, it gives me the new one. See, 4x cubed. That means I can now write denominator is just u to the power 2 because I choose x to the power 4 plus 1 is my u. And my 4x dx, what is my 4x cubed dx? It's just du. 4x cubed dx is my du. So I really replace my x variable to u, and my u variable is easy to integrate. So it's u minus 2 du. How do you integrate? You add 1 to the power, you divide by the same power. So that will be u minus 1 plus c. So it's a minus 1 over u, but u is x to the power 4 plus 1. That's my 1 over u minus plus c. That's the integration of the one I started. Okay. It's clear. I'm going to go to part C. Okay. Part C is 9r to the power 2, 1 minus r cube. Okay, I'm going to use it here. See. All right. 9r to 1 minus r to the cube. That's correct. Okay. dr. So again, the substitution, the common substitution is for something in the square root sign. The square root, and inside the square root, I have 1 minus r cube. I go with that. Du over dx is negative 3r2. I have 9r2. That is okay. I can write it like this. Negative 3, if I take negative 3 out, I can write it's negative 3r2 dr. Because if I simplify negative 3 with negative 3, I can get 9. The denominator is 1 minus r cube, but it's u square root. So now I can replace my numerator because it's just du. See? Negative 3r to the power 2 here. So if I bring dx, it's just du. So you can see here, negative 3r to the power 2 dr, negative 3r to the power d. Actually, this should be dr. Okay? dr. Same thing here. So it's like du. I have square root of here. So check it. So you kind of create everything. You recover everything with this variable. You recover integrand. All the variable you have are changed to all the expressions, numerator and denominator, with variable y replaced to variable u. Okay. But of course, you may have some constant, negative 3 here, or half, or whatever. It doesn't really matter. And you have integration u negative half, because square root of it's in the denominator. So negative 3, you add 1, so it's become half, divide by half, plus c. So finally, you can write it's negative 6 square root of u plus c. That's the answer for C. I'm going to go to D. So I'm going to erase this on the top, okay? So that I can just copy that. All right. So cosecant square d theta, do 2 theta, cotangent 2 theta. I know something, the cotangent and cosecant. The derivative of cotangent is negative cosecant theta, remember? So because of that, I can choose cosecant square d theta, cotangent 2 theta, I'm sorry, 2 theta, cotangent 2 theta d theta. I choose my u to be cotangent 2 theta because I know if I take the derivative with respect to theta minus cosecant square 2 theta, because derivative of cotangent is cosecant square minus, and you have to differentiate 2 theta. 2 theta, if you differentiate with theta, it's just 2, okay? So that's mean really du over 2. If I divide by negative 2, it's a negative half, cosecant square 2 theta d theta. So you can see here, I have in the right hand side is exactly I have here, cosecant square 2 theta d theta. So I'm gonna now write my I as cotangent 2 theta is just u. The other part you can see from, I highlighted using green color, it's negative du over 2. I can put 2 here. It's a half. It's negative half u to the power 2 over 2 plus c. I got the integration. It's a hard trig integration, but I got it as cotangent square 2 theta, because u is cotangent 2 theta. I have 4 in the denominator plus c. Clear? I hope it's very clear how the substitution will for D, part D, okay? I use the substitution as cotangent 2 theta. That's my U. Right. Secant square 3x plus 2. Actually, we did similar question. Remember, secant square 5x minus something in here. Actually, I can use the substitution to do that. I told you that. I explained that. But I can, do without that as well. But this time I use the substitution. Okay. It's not. I can understand. So here the idea is E secant square 3x plus 2 dx. You can use u as 3x plus 2. If you differentiate with respect to x, it's just 3. Du over 3 is dx. That means if we choose this to be I, the integration is secant square, because everything 3x plus 2 now is u. And what is dx? 3u du over 3. So you just divide by, actually 3 is the derivative of 3x plus 2. So integration of secant square is tan u, you have 1 over 3 plus c, but actually u is 3x plus 2. You have 3. You just really divide by 3. So remember, that's what we did in the last part. Question number 11. Okay. All right. F, G, and H. I think H is really challenging. Maybe F as well. Yeah, F, I really like that question. F gives you some challenging. You will see that, okay? Because if you take the substitution as x to the power 2 plus 1, like here, so I'm talking about F. So in the F, you can think it's, okay, I choose I, x to the power 3, square root of x to the power 2 plus 1, right? So, okay, I can choose this one as x to the power 2 plus 1. But if you take the derivative, when you take the derivative, you really see it's just 2x. It don't give you x cube, right? It doesn't give you x cube. So now I can write it like this. I know square root, inside the square root is just u, the u square root. That's how I choose the substitution. And I have x to the power 2, I can keep like that. And I write x dx. Actually, I had x cube. Okay, I had x cubed. I write it as x to the power 2 x is x cubed dx. Same thing. Okay? When I do that, du over 2 is x dx. So I can replace, I don't know still x to the power 2, I have to replace it. But x dx, I can replace with du over 2. I can write it. Right? This is tricky. Now you can see, I have to replace x to the power 2. I still have to replace it. So to do that, you can think, okay, x to the power 2, you can replace with the original substitution one more time. You have used the original substitution one more time. So x to the power 2 is really u minus 1. So it's like half u minus 1, that's x to the power 2, square root of u, which is power half d. That is how you will do it. Now you have to simplify this one little bit. You multiply with u half, u to the power half with u, give you 1 plus half, which is 3 over 2. This is u half. This all you can integrate because of just a power rule. Half. You add 1, which is 5 over 2. 5 over 2. 3 over 2. 3 over 2 plus 0. And again, you can bring, everything. Two cancel out with this. It's like u 5 over 2 over 5. 3 over 2 over 3 plus arbitrary constant. So I hope you understand the idea here. Can't really replace everything just by substitution one time. You replace the inside the square root with u. You have to replace x to the power 2 also with u minus 1. Okay, I use that. That means I use the same substitution. Okay. Same technique you have to use for last question. For last question, I can choose the same substitution like 2x plus 1. U is 2x plus 1. If I use that way, du over dx is 2. This means du over 2 is my dx. So that means I equal square root of u. This is square root of u, but I have x there. What is x really? So you have to replace x with this again. So x is, if you use that, it's u minus 1 over 2. That's x. You bring this to other side and divide by 2. So you have to use that. Okay, this is your x. That's your x. Dx, you have to replace dx as well. It's really du over 2. That means you have to take the 2 out. It's 1 over 4. U minus 1. U to the power half here. It's 1 over 4. Integration u 3 over 2. U 1 over 3. It's similar to this one. See, you have only half. If you think about this part, same as this one. So it's just the previous one, you divide by 2 one more time, because it's just 2 over there. So I can write 2 5 over 2 over 10, u 3 over 2 over 6 plus 6. Just by looking at the part G, which is the last one. You just, because you had half here, now you have 1 over 4, which means now divide the previous answer by 2. You don't need to divide C by 2. You can, C is just an arbitrary constant. It's like, it's not the same C you have here, even though I write the same C. It's a different arbitrary constant. You can put a C dash if you want. All right. I hope it's clear, the last video, that all 4 videos explain 13 questions in this practice problem set. Okay. Go over the questions a few more times, find similar questions to this from your textbooks and other resources you have. It will really give you some practice.